Welcome to Sleepy Science Hub. I'm so glad you found your way here tonight, to this peaceful corner where science meets the gentle art of rest. As you settle into your most comfortable position, wherever you might be in the world, take a moment to let me know in the comments where you are and what time it is as you listen. There's something wonderfully comforting about knowing we're sharing this moment of learning together, connected across distances by our curiosity about the universe around us. Tonight, we're going to embark on a gentle journey to our nearest star, the Sun, to understand one of space's most beautiful phenomena, solar flares. But don't worry about any dramatic explosions or dangerous radiation. We're approaching this topic like peaceful observers, watching the sun's magnetic fields dance and reconnect like aurora in slow motion, witnessing the graceful flow of energy that connects our star to our planet in ways both subtle and profound. Now, get comfortable. Adjust your pillows, pull your blankets close, and let your breathing settle into its natural rhythm. Take a slow breath. Feel your body releasing the tension of the day, and let's begin this tranquil journey through the garden of our solar system's heart. As you lie there in comfort, your breathing beginning to slow and deepen, imagine yourself gently floating in the perfect darkness of space, but not the cold, hostile void that science fiction might portray. Instead, picture yourself suspended in a warm, protective cocoon of invisible forces, surrounded by the gentle light of distant stars and bathed in the soft, constant glow of our own sun, which hangs before you like a magnificent golden garden in the cosmic darkness. From this peaceful vantage point, 93 million miles from the sun's surface, our star appears not as the blazing, dangerous ball of fire that we might fear, but rather as a living, breathing entity of remarkable gentleness and consistency. The light that reaches you here has been traveling for just over 8 minutes from the sun's surface, carrying with it not only the warmth and energy that makes life possible on Earth, but also the stories of countless intricate processes happening within our star's vast, layered atmosphere. The sun that you observe from this restful distance is actually a middle-aged star, roughly 4.6 billion years old, settled into a period of remarkable stability that has persisted for eons and will continue for billions of years to come. Unlike the young, energetic stars that burn hot and bright for relatively brief cosmic moments, or the ancient, cooling stars nearing the end of their lives, our sun represents stellar maturity, a perfect balance of size, temperature, and magnetic activity that creates conditions ideal for supporting the delicate chemistry of life. As your eyes adjust to this cosmic perspective and your breathing synchronizes with the slow, eternal rhythms of space, you begin to notice that the sun's surface is not uniform. Rather than a smooth, featureless sphere, the photosphere, the visible surface of the sun, reveals itself as a constantly shifting tapestry of subtle variations in brightness and texture. These variations change so gradually that watching them is like observing clouds slowly transforming shape on a summer afternoon, or like watching the gentle play of light and shadow on the surface of a calm lake. The granular texture that becomes apparent as you observe more closely results from convection currents, vast cells of hot plasma rising from deep within the sun and cooling as they reach the surface before sinking back down again. Each of these granules is larger than entire countries on Earth, yet they appear and disappear with the gentle patience of natural processes unfolding over periods of minutes to hours. The overall effect is like watching a vast field of golden wheat swaying in an imperceptible breeze, each stalk moving independently, yet contributing to a larger pattern of harmonious motion. Scattered across this gently undulating surface, you notice regions that appear slightly darker than their surroundings. These are sunspots, areas where intense magnetic fields have temporarily cooled the surface temperature by a few hundred degrees. Far from being flaws or imperfections, these sunspots represent the visible manifestation of the sun's complex magnetic personality, appearing and disappearing in cycles that span approximately 11 years. During periods of high solar activity, the sun's surface might host dozens of these magnetic gardens, while during quieter periods, the surface may remain almost entirely clear. The beauty of sunspots lies not in their darkness, but in their intricate structure and the way they evolve over time. The largest sunspot groups can persist for weeks or even months, slowly changing shape as magnetic forces beneath the surface shift and reconfigure. Watching their evolution is like observing the slow growth and transformation of flowers in a garden, each spot developing its own characteristic shape and personality before eventually fading away as the magnetic fields that created it disperse back into the general solar atmosphere. But the sun's magnetic personality extends far beyond these visible surface features. Rising above the photosphere, invisible to normal observation but revealed through special filters and instruments, lies the chromosphere, a layer of the solar atmosphere where temperature paradoxically increases with altitude and where the first hints of the sun's magnetic complexity become apparent. In this region, magnetic field lines arch and loop through the thin plasma like luminous bridges connecting different regions of the solar surface. These magnetic field lines, though invisible to our imaginary floating perspective, shape and guide the flow of charged particles throughout the solar atmosphere with the gentle persistence of streams channeling water through a landscape. They create a three-dimensional architecture of invisible pathways that extends from deep within the sun all the way out into the solar wind that fills the space between planets. Understanding these magnetic highways is crucial to understanding how solar flares form, because it is along these pathways that energy accumulates, builds tension, and eventually releases in the graceful displays we call solar flares. Above the chromosphere lies the corona, the sun's outer atmosphere, a realm so hot that it glows with temperatures exceeding 1,000,000 degrees, yet so tenuous that it has less density than the best vacuum we can create on Earth. The corona extends millions of miles from the sun's surface, its shape constantly changing as magnetic fields reorganize and solar wind carries material away into space. During total solar eclipses, when the moon temporarily blocks the bright disk of the sun, the corona becomes visible as a shimmering, pearl-colored halo that demonstrates the dynamic, ever-changing nature of our star's extended atmosphere. As you continue to observe from your peaceful vantage point in space, your breathing now slow and regular as a tide, you begin to appreciate that the sun operates on multiple timescales simultaneously. The nuclear fusion reactions in the core that power everything we observe happen millions of times per second, yet the energy they produce takes hundreds of thousands of years to work its way from the core to the surface. The granulation patterns on the photosphere change over minutes and hours, while sunspot cycles unfold over years and decades. Solar flares themselves represent sudden releases of energy that can occur in minutes, yet they result from magnetic configurations that build up over days, weeks, or months. This multiplicity of timescales creates a kind of cosmic symphony where different processes contribute their own rhythms to an overall harmony that has persisted for billions of years. The sun's consistency, its ability to provide steady energy output despite the incredible complexity of processes within it, represents one of nature's most remarkable examples of dynamic stability. Like a master musician who can improvise endless variations on a theme while maintaining the underlying melody, the sun maintains its essential character while constantly adapting to the changing configurations of its magnetic fields and plasma flows. The magnetic fields that permeate the solar atmosphere arise from the same basic physical processes that create the magnetic field around a simple bar magnet, but scaled up to sizes and complexities that dwarf anything we experience on Earth. Deep within the sun, the differential rotation, the fact that the equatorial regions rotate faster than the polar regions, stretches and twists magnetic field lines like rubber bands being wound tighter and tighter. This process, called the solar dynamo, operates on timescales of years and decades, gradually building up the magnetic complexity that provides the energy for solar flares. The plasma that fills the solar atmosphere consists of electrons and protons that have been stripped apart by the intense heat, creating a state of matter that is both more fluid than gas and more responsive to magnetic forces than any material we encounter in everyday life. This plasma flows along magnetic field lines like water flowing through invisible pipes, but it can also push against and reshape those same magnetic fields when pressure builds up sufficiently. The delicate interplay between plasma flow and magnetic fields creates a constantly evolving system where small changes can cascade into larger reorganizations. Yet the overall system maintains its stability through self-regulating feedback mechanisms. As your perspective from this cosmic distance allows you to take in the sun as a complete system, you begin to understand that solar flares are not random explosions or signs of stellar instability, but rather natural expressions of the magnetic energy that builds up through the normal operation of solar processes. Like flowers blooming in a garden or waves forming on the surface of a lake, solar flares represent the sun's way of releasing accumulated magnetic tension and returning to a more stable configuration. The energy that will eventually power solar flares begins its journey in the nuclear furnace of the sun's core, where hydrogen atoms fuse into helium under conditions of incredible temperature and pressure. But that energy must travel through thousands of miles of stellar material before it can participate in the magnetic processes that create flares. The journey from core to corona involves multiple transformations, from gamma rays to visible light, from radiation to convection, from thermal energy to magnetic energy. Each step in the process following natural laws that ensure the sun's overall stability while allowing for the beautiful complexity of solar activity. The solar wind, the constant stream of charged particles flowing away from the sun, carries with it information about conditions in the solar atmosphere and extends the sun's influence throughout the solar system. This wind interacts with planetary magnetic fields, creating the magnetospheres that protect planets like Earth from direct exposure to solar radiation. The solar wind also provides the medium through which disturbances from solar flares can travel, carrying the effects of solar activity to the far reaches of the solar system at speeds of hundreds of miles per second. From your peaceful observation point, you can sense that the sun exists within a larger cosmic context, influenced by its journey through the galaxy and by the gravitational effects of nearby stars. The solar system as a whole moves through regions of space with different densities of cosmic rays and interstellar material, creating long-term variations in the solar environment that operate on timescales of millions of years. These galactic influences add another layer to the complex symphony of forces that shapes solar activity and remind us that our star, for all its apparent isolation in space, participates in the larger community of stars that make up our galaxy. The light and warmth that the sun provides to Earth represent only a tiny fraction of its total energy output. Yet this fraction is precisely calibrated to maintain the temperature range that allows liquid water to exist on our planet's surface. This remarkable coincidence, that Earth orbits at just the right distance to receive just the right amount of solar energy, creates what astronomers call the habitable zone, a narrow band around the sun where conditions are favorable for life as we know it. As you rest in this cosmic perspective, your breathing now deep and peaceful, you can appreciate that the story of solar flares is ultimately a story about the sun's magnetic personality, its tendency to create complex, beautiful patterns of magnetic fields that occasionally reorganize themselves in displays of gentle power. These reorganizations connect our star to our planet through invisible threads of magnetic influence, creating the conditions for some of Earth's most beautiful natural phenomena, while demonstrating the interconnectedness that characterizes our solar system. The sun's 11-year activity cycle, during which the number and intensity of solar flares rises and falls in a predictable pattern, reflects the deep rhythms of the solar dynamo and provide the temporal framework for understanding solar behavior. During solar maximum, when flare activity peaks, the sun's magnetic field configuration becomes highly complex, with numerous active regions hosting the twisted magnetic structures that give rise to flares. During solar minimum, the magnetic field simplifies, flare activity decreases, and the sun enters a period of relative calm that can last for several years. Understanding that solar flares emerge from this natural cycle of magnetic complexity and simplification helps us appreciate them as expressions of stellar health rather than signs of stellar distress. Just as seasons change on Earth in response to our planet's orbital motion, solar activity changes in response to the internal dynamo processes that regenerate and reorganize the sun's magnetic field. These changes represent the sun's way of maintaining its long-term stability while accommodating the inevitable accumulation and release of magnetic energy that results from its rotation and internal structure. As you continue to float peacefully in the cosmic darkness, your breathing now synchronized with the eternal rhythms of space. Let your awareness gently descend into the heart of our star, where the story of every solar flare truly begins. Deep within the sun's core, in a region smaller than the distance from Earth to the moon, yet containing more than half of the sun's total mass, the most fundamental process in our solar system unfolds with patient, methodical precision that has continued unchanged for over 4 billion years. Picture yourself drifting slowly inward through layers of increasingly dense stellar material, each layer representing a different chapter in the sun's energy production story. The journey inward is like sinking through the depths of a luminous ocean, with a pressure and temperature increase gradually, but dramatically with each mile of descent. The environment here exists in a state so different from anything on Earth that it requires a complete reimagining of what matter can become when subjected to the extreme conditions that exist at the heart of a star. At the very center of this stellar furnace, in a sphere roughly 200,000 miles in diameter, the temperature reaches 15 million degrees Celsius, hot enough to strip electrons from atoms and create a soup of free-floating atomic nuclei and electrons that physicists call plasma. Yet despite these extreme conditions, the nuclear fusion reactions that power the sun proceed with remarkable gentleness and control, releasing energy at a rate that could power human civilization for billions of years while maintaining the precise balance necessary to keep our star stable and long-lived. The fusion process itself is a dance of incredible delicacy, where hydrogen nuclei, single protons, must overcome their natural electromagnetic repulsion to get close enough for the strong nuclear force to bind them together. This happens not through violent collisions, but through a quantum mechanical process called tunneling, where particles can essentially slip through energy barriers that should be insurmountable according to classical physics. The probability of any individual proton-proton collision resulting in fusion is extraordinarily small, yet with countless trillions of such collisions occurring every second, the overall rate of energy production remains steady and predictable. As your consciousness settles into this realm of extreme physics, your breathing becoming ever more peaceful and regular, you can appreciate that each fusion reaction converts a tiny amount of matter directly into energy according to Einstein's famous equation, E equals mc squared. The amount of mass converted is minuscule, less than 1% of the original protons. But the speed of light squared is such an enormous number that even this tiny mass conversion releases tremendous amounts of energy. For hydrogen nuclei combine to create one helium nucleus, with the small difference in mass becoming pure energy that will eventually find its way to the sun's surface and beyond. The energy released by nuclear fusion emerges initially in the form of gamma rays, extremely high-energy photons that represent the most concentrated form of electromagnetic radiation. These gamma rays begin an epic journey from the core toward the surface that will take hundreds of thousands of years to complete, not because they travel slowly, but because the path they must follow is incredibly complex and circuitous. Each gamma ray can travel only a few millimeters before being absorbed by an atom in the dense stellar material, only to be re-emitted a fraction of a second later, usually as lower energy photons. This process of absorption and re-emission creates what physicists call a random walk, where each photon follows a zigzag path through the stellar interior, sometimes moving outward toward the surface, sometimes moving sideways or even back toward the center. The overall effect is like watching a leaf slowly work its way downstream in a river with countless obstacles. The general direction is clear, but the actual path involves countless detours and redirections. This random walk is what gives the sun's energy output its remarkable stability, as it acts like a vast reservoir that smooths out any fluctuations in the nuclear fusion rate. The region surrounding the core, extending outward for about 200,000 miles, is called the radiative zone, where energy transport occurs entirely through this process of photon absorption and re-emission. The material in this zone is so dense and hot that it behaves more like a solid than a gas, even though it's technically a plasma. The temperature and pressure decrease gradually with distance from the center, but the conditions remain far too extreme for any chemistry as we know it to exist. Instead, energy flows outward through pure radiative processes, with each layer of material slightly cooler than the layer beneath it. As you drift peacefully through this radiative zone, imagining the countless photons around you each on their own random journey toward the surface, you begin to understand how the sun's interior acts as a vast energy storage and regulation system. The enormous time delay between energy production in the core and energy release at the surface means that the sun's brightness depends not on today's fusion rate, but on the fusion rate averaged over hundreds of thousands of years. This temporal smoothing effect is what allows the sun to maintain such stable energy output despite the quantum mechanical uncertainties inherent in individual fusion reactions. The boundary between the radiative zone and the next layer outward marks a fundamental transition in how energy moves through the sun. At about 70% of the distance from the center to the surface, the material becomes cool enough and thin enough that radiative energy transport becomes inefficient. The photons still carry energy, but they can no longer keep pace with the energy flowing outward from the core below. When this happens, the stellar material begins to develop another form of energy transport, convection. The convection zone extends from about 200,000 kilometers below the surface all the way to the photosphere itself, representing nearly 30% of the sun's radius. In this region, energy is transported not by photons alone, but by the physical motion of hot plasma rising upward and cooler plasma sinking downward. This process is fundamentally similar to the convection that occurs in boiling water or in Earth's atmosphere, but scaled up to sizes that dwarf entire planets and operating under conditions of temperature and pressure that exist nowhere else in our solar system. Picture yourself now floating within one of these convection cells, surrounded by plasma that is rising slowly toward the surface at speeds of perhaps a few meters per second, about the speed of a gentle walking pace. The material around you is still incredibly hot by Earth standards, with temperatures of several thousand degrees, but it represents the coolest environment you would encounter anywhere within the sun's interior. The plasma flows upward, not in violent eruptions, but with the steady persistence of warm air rising on a summer day, carrying energy from the deeper layers toward the surface through bulk motion rather than radiation alone. The convection cells within which you're traveling are enormous by terrestrial standards, with typical diameters comparable to the size of Earth's continents and circulation patterns that persist for months or years before reorganizing into new configurations. These cells stack upon each other in a complex three-dimensional pattern, with smaller cells embedded within larger ones and flow patterns that change gradually as the plasma responds to the varying conditions at different depths within the convection zone. As your breathing continues to slow and deepen, matching the patient rhythm of these vast circulation patterns, you can appreciate how the convection zone serves as the interface between the sun's deep interior and its visible surface. The energy that has taken hundreds of thousands of years to work its way outward through the radiative zone completes its journey to the surface in a matter of weeks or months through convective transport. This final stage of energy transport is what creates the granular texture visible on the sun's surface as convection cells reach the photosphere and release their thermal energy into space. The interaction between convection and magnetic fields in this zone is crucial for understanding how solar flares eventually form. The flowing plasma acts like a dynamo, generating and amplifying magnetic fields through the same basic process that creates Earth's magnetic field, but on a much larger scale and with much greater complexity. As plasma moves through existing magnetic fields, it drags the field lines along with it, stretching and twisting them into increasingly complex configurations that store enormous amounts of magnetic energy. The differential rotation of the Sun, the fact that different latitudes rotate at different speeds, adds another layer of complexity to the magnetic field generation process. The equatorial regions of the Sun complete one rotation in about 25 days, while the polar regions take about 35 days. This difference in rotation rate continuously shears magnetic field lines, stretching them in the east-west direction and creating the conditions necessary for the solar dynamo to operate. The solar dynamo is not a machine in any conventional sense, but rather a self-sustaining process where motion generates magnetic fields, and magnetic fields influence motion in ways that maintain and amplify the magnetic field generation. This process operates on multiple timescales simultaneously. Individual convection cells change over months, while the overall magnetic field configuration follows an 11-year cycle, and the dynamo process itself has persisted for billions of years with remarkable consistency. Deep within the convection zone, magnetic field lines become anchored to the flowing plasma and are carried along by the convective motions. Imagine these field lines as invisible elastic bands that can be stretched and twisted by the plasma flow, but cannot be broken. As convection cells rise and fall, rotate and reorganize, they continuously deform the magnetic field structure, sometimes in ways that increase magnetic energy, and sometimes in ways that allow stored energy to be released. The magnetic fields generated in the convection zone don't remain hidden in the interior, but gradually work their way toward the surface, where they will eventually emerge into the solar atmosphere and create the complex magnetic structures that give rise to solar flares. This migration of magnetic flux from the interior to the surface happens over timescales of months to years, representing another temporal buffer that contributes to the generally gradual and predictable nature of solar activity cycles. As magnetic field lines approach the surface, they begin to interact with the decreasing density and temperature of the outer layers of the convection zone. The plasma becomes progressively less dense as it rises, while the magnetic field strength can remain relatively constant, leading to situations where magnetic pressure begins to dominate over gas pressure. When this happens, the magnetic fields can control the motion of the plasma rather than being controlled by it, setting the stage for the complex magnetic structures that emerge into the solar atmosphere. The top of the convection zone, where it meets the photosphere, represents another crucial boundary in the Sun's structure. Here, the plasma becomes cool enough and thin enough that it transitions from being completely opaque to being partially transparent. This transition zone, only a few hundred kilometers thick, is where the Sun's interior energy finally escapes in a space as visible light, and where the magnetic fields generated deep in the convection zone first become observable from Earth. The temperature structure through the convection zone shows a steady decrease from the bottom to the top, but the rate of decrease is precisely controlled by the convective process itself. As plasma rises and expands in the decreasing pressure environment, it cools adiabatically, following the same thermodynamic process that causes rising air masses in Earth's atmosphere to form clouds and precipitation. This self-regulating temperature gradient ensures that convection continues to transport energy efficiently while maintaining the thermal structure necessary for stable stellar operation. The chemical composition of the convection zone reflects billions of years of nuclear processing in the core, but with important modifications due to convective mixing. Elements heavier than hydrogen and helium, created by nuclear fusion processes, are gradually mixed throughout the convection zone by the stirring action of convective flows. This mixing process is what allows astronomers to study the Sun's internal nuclear processes by analyzing the composition of its surface layers. The acoustic properties of the convection zone create a complex environment where sound waves can propagate in ways that reveal information about the Sun's internal structure. These acoustic waves, generated by the turbulent motions associated with convection, create a kind of stellar seismology that allows scientists to probe conditions deep within the Sun. The study of these solar oscillations has revolutionized our understanding of stellar interiors and confirmed many theoretical predictions about how stars like the Sun operate. As you continue to drift peacefully through this realm of gentle giants, convection cells larger than planets, magnetic fields stronger than any created on Earth, and energy flows that dwarf all human technology, your breathing naturally synchronizes with these vast stellar rhythms. The convection zone represents the sun's way of managing the enormous energy flux from its nuclear core, organizing that energy into structured flows that can transport it efficiently to the surface while generating the magnetic complexity that makes solar activity possible. The boundary layer between the convection zone and the radiative zone below, called the tachocline, plays a special role in the solar dynamo process. In this narrow region, the differential rotation that characterizes the convection zone meets the more uniform rotation of the radiative interior, creating strong shear flows that are particularly effective at amplifying magnetic fields. Many scientists believe that the tachocline is where the strongest magnetic fields in the sun are generated and stored before eventually rising to the surface. The timescales associated with energy transport in the convection zone represent a middle ground between the extremely long radiative diffusion times in the deep interior and the rapid light travel times in the solar atmosphere. Energy can move from the bottom to the top of the convection zone in a matter of weeks, making this region much more responsive to changing conditions than the radiative interior, but still providing substantial temporal smoothing compared to the atmospheric layers above. The pressure environment in the convection zone decreases by many orders of magnitude from bottom to top, creating conditions where the same physical processes must operate under vastly different circumstances. The plasma at the bottom of the convection zone exists under pressures comparable to those at the center of Jupiter, while the plasma at the top approaches pressures similar to Earth's atmosphere. This enormous pressure range requires convective flows to continuously adjust their characteristics as they rise and fall through the zone. As you prepare to continue your journey outward from this quiet furnace toward the more dynamic regions of the solar atmosphere, you carry with you an appreciation for the patient, methodical processes that power our star. The nuclear fusion in the core, the radiative transport through the interior, and the convective mixing in the outer layers all work together to create a remarkably stable and long-lived energy source that has maintained nearly constant output for billions of years while generating the magnetic complexity that makes solar flares possible. As you drift peacefully from the deep convection zone toward the sun's visible surface, your consciousness floating like a gentle current in an ocean of luminous plasma, you begin to witness one of nature's most beautiful and intricate phenomena, the emergence of magnetic field lines from the solar interior into the realm, where they can finally express their accumulated energy in the graceful displays we call solar flares. This transition zone, where the sun's hidden magnetic architecture becomes visible, unfolds before you like a vast garden of light, where invisible forces sculpt streams of glowing plasma into patterns of extraordinary beauty and complexity. Picture yourself now suspended just beneath the photosphere, in a realm where the plasma around you has become thin enough to be partially transparent, yet still dense enough to glow with its own internal heat. Here, the temperature has cooled from the millions of degrees of the deep interior to a mere few thousand degrees, still hot enough to vaporize any material known on Earth, but cool enough that hydrogen atoms can begin to recombine with electrons, creating the conditions necessary for the sun's visible light to escape into space. The convection currents that have carried you upward from the depths now reach their final destination, emerging at the photosphere as the granulation pattern that gives the sun's surface its characteristic mottled appearance. Each granule represents the top of a convection cell, where hot plasma rises to the surface, spreads outward, cools by radiating energy into space, and then sinks back down at the granule boundaries to complete the circulation cycle. These granules appear and disappear with the rhythm of a slow heartbeat, each one persisting for about 10 to 20 minutes before being replaced by new patterns of convective flow. But woven throughout this convective pattern, invisible to normal observation but revealed through the special filters of scientific instruments, are the magnetic field lines that carry the memory of dynamo processes occurring deep within the convection zone. These field lines rise through the solar interior like invisible rivers of force, guiding the flow of electrically charged plasma and creating structures that extend far above the visible surface into the solar atmosphere. Understanding these magnetic rivers is crucial to understanding how solar flares form, because they provide both the energy and the architecture necessary for these beautiful displays of stellar activity. As your breathing becomes deeper and more regular, synchronized with the slow rhythm of these rising magnetic structures, you can begin to sense the three-dimensional complexity of the magnetic field configuration just beneath the solar surface. Unlike the relatively simple dipolar field of a bar magnet, the sun's magnetic field consists of countless individual flux tubes, bundles of magnetic field lines that rise through the convection zone like luminous cables carrying energy from the deep interior toward the surface and beyond. Each magnetic flux tube begins its journey deep within the convection zone, where dynamo processes twist and amplify weak seed fields into strong, coherent structures. The magnetic field lines within these tubes are parallel to each other and point in the same direction, creating a concentrated bundle of magnetic force that can maintain its integrity even as it rises through hundreds of thousands of kilometers of turbulent convective flow. The plasma within and around these flux tubes follows the magnetic field lines, creating channels of flow that can persist for weeks or months as the magnetic structure slowly rises toward the surface. The buoyancy that drives magnetic flux tubes toward the surface arises from the same principle that causes bubbles to rise in a liquid. Magnetic pressure reduces the density of plasma within the flux tube, making it lighter than the surrounding material and causing it to rise through the solar interior. This magnetic buoyancy effect is subtle but persistent, operating over timescales of months to years as magnetic structures work their way from their generation sites deep in the convection zone to their emergence points of the photosphere. As magnetic flux tubes approach the surface, they begin to interact with the stratified atmosphere above the photosphere, where density decreases rapidly with height and where the magnetic field can begin to dominate over gas pressure. This transition from a gas pressure-dominated environment to a magnetic pressure-dominated environment marks the beginning of the solar atmosphere proper, where magnetic forces shape and control plasma flows in ways that create the spectacular structures visible in solar images. The emergence of magnetic flux through the photosphere happens gradually and gently, like flowers slowly blooming in a garden. The first signs of emerging magnetic field often appear as small, dark areas called magnetic knots or micropores, where the magnetic field is strong enough to inhibit convective heat transport and cause local cooling of the photosphere. These tiny magnetic features may be only a few hundred kilometers across, small by solar standards, but still larger than most countries on Earth. As more magnetic flux emerges through the same area, these small magnetic knots can grow and merge to form larger structures. When a magnetic field strength reaches a few thousand times stronger than Earth's magnetic field, the cooling effect becomes pronounced enough to create the dark areas we call sunspots. But even the formation of sunspots happens gradually, with magnetic flux continuing to emerge over periods of days or weeks, slowly building up the field strength and expanding the area of magnetic influence. The geometry of emerging magnetic flux creates fascinating three-dimensional structures that extend far above the visible solar surface. When a magnetic flux tube reaches the photosphere, it typically emerges as a pair of regions with opposite magnetic polarity, one where field lines emerge from the surface, positive polarity, and another where field lines dive back into the surface, negative polarity. The field lines connecting these two regions arch high above the photosphere, creating magnetic loops that can extend for tens or hundreds of thousands of kilometers into the solar atmosphere. These magnetic loops are invisible to the naked eye, but can be traced by observing the motion of plasma within them. The electrically charged particles that make up solar plasma are constrained to follow magnetic field lines, so the shape of the magnetic loops can be inferred from the patterns of glowing plasma that outline them. An image is taken with special filters that isolate specific wavelengths of light emitted by different ions in the solar atmosphere. These magnetic loops appear as graceful arches and arcades that span vast regions of the solar surface. As you float peacefully in this realm, where magnetic forces begin to dominate over gas pressure, your breathing now slow and natural as ocean tides, you can appreciate the delicate balance that allows these magnetic structures to maintain their coherence while supporting the flow of plasma along their length. The magnetic field lines act like invisible pipes or channels that guide plasma flow. But unlike rigid pipes, these magnetic channels can flex and adjust their shape in response to changing conditions while maintaining their essential connectivity between different regions of the solar surface. The plasma that flows along these magnetic field lines carries energy from one part of the solar atmosphere to another, creating a complex system of energy transport that operates entirely through electromagnetic forces. Hot plasma arising from the photosphere along one magnetic field line can travel through the solar atmosphere and deposit its energy at a different location by flowing down another field line, creating thermal and dynamic connections between widely separated regions of the solar surface. The temperature structure of the solar atmosphere shows a remarkable and initially puzzling increase with height above the photosphere. While the visible surface has a temperature of about 5,800 degrees Celsius, the chromosphere above it reaches temperatures of 10,000 to 20,000 degrees, and the corona beyond that reaches temperatures exceeding 1 million degrees. This temperature increase with height, opposite to what we would expect from a simple cooling atmosphere, is maintained by energy transport along magnetic field lines and by the gradual release of magnetic energy through processes that will eventually lead to solar flares. The chromosphere, extending for about 2,000 kilometers above the photosphere, represents the first layer of the solar atmosphere where magnetic effects become clearly visible. Here, magnetic field lines channel plasma into long, thin structures called spicules that rise from the solar surface like luminous grass swaying in an invisible breeze. These spicules are typically about 500 kilometers wide and can extend for 10,000 kilometers above the surface, appearing and disappearing with lifetimes of about 10 to 15 minutes. The motion of plasma within spicules reveals the dynamic nature of magnetic field lines in the solar atmosphere. Rather than static structures, these magnetic channels constantly adjust their configuration in response to changing conditions at their foot points in the photosphere and to the pressure of plasma flowing within them. The result is a constantly evolving forest of magnetic structures that transport energy and material between the solar surface and the upper atmosphere, while creating some of the most beautiful displays in the solar system. Above the chromosphere lies the transition region, a narrow layer where temperature increases rapidly from 20,000 degrees to over 100,000 degrees over a distance of only a few hundred kilometers. This dramatic temperature rise occurs because magnetic field lines in this region begin to reconnect and release stored energy through processes that heat the local plasma to extreme temperatures. The transition region represents the beginning of the realm where magnetic energy accumulated over long periods can be released in the sudden bursts that characterize solar flares. The corona, extending millions of kilometers above the solar surface, is entirely dominated by magnetic forces and represents the region where the most spectacular expressions of solar magnetic activity occur. The extremely low density of coronal plasma, less than 1/billionth the density of Earth's atmosphere at sea level, means that magnetic pressure far exceeds gas pressure, allowing magnetic field lines to maintain complex three-dimensional structures that would be impossible in denser environments. Coronal magnetic field lines organize themselves into large-scale structures called coronal loops, which can be hundreds of thousands of kilometers long and persist for days or weeks before reconfiguring. These loops are outlined by plasma heated to millions of degrees, making them visible in extreme ultraviolet and X-ray images that reveal the sun's magnetic skeleton. The plasma within coronal loops flows along the magnetic field lines at speeds of tens of kilometers per second, carrying energy and material in circulation patterns that connect different regions of the solar surface. The magnetic energy stored in coronal loops represents the accumulated result of weeks or months of magnetic flux emergence from the solar interior, with energy gradually building up as magnetic field lines are twisted and stressed by motions at their foot points in the photosphere. This energy accumulation process happens so gradually that it's usually imperceptible, like the slow winding of a spring or the gradual inflation of a balloon. The energy builds up not through violent processes, but through the patient persistence of small motions and adjustments that eventually create conditions ripe for magnetic reconnection. As you continue to observe this magnetic landscape from your peaceful vantage point, your consciousness now fully attuned to the slow rhythms of magnetic evolution, you begin to understand that the solar atmosphere is essentially a magnetic plasma laboratory where fundamental physical processes play out on scales and under conditions that cannot be replicated anywhere else in the solar system. The interaction between magnetic fields and electrically charged particles creates phenomena that demonstrate basic principles of electromagnetism while producing displays of beauty that rival any terrestrial aurora. The differential rotation of the Sun continues to influence magnetic field evolution even after flux tubes have emerged into the atmosphere. Since different latitudes rotate at different rates, magnetic field lines connecting regions at different latitudes experience continuous shearing motions that gradually increase their complexity and energy content. This shearing process is particularly important for creating the twisted magnetic configurations that are most likely to undergo the reconnection events that trigger solar flares. The photospheric motions that drive magnetic evolution in the solar atmosphere are remarkably gentle by most standards, typically involving velocities of only a few kilometers per second, about the speed of a brisk walk. Yet when these motions persist for days or weeks, they can transport magnetic flux over vast distances and create complex field configurations that store enormous amounts of energy. It's another example of how the Sun achieves powerful effects through patient, persistent processes rather than sudden, violent actions. The magnetic field topology in active regions, areas of enhanced magnetic activity on the solar surface, often exhibits a characteristic evolution from simple to complex configurations over periods of days to weeks. Newly emerged flux typically forms relatively simple bipolar structures with clean field line connections between positive and negative polarity regions. As photospheric motions shear and twist these field lines, the magnetic topology becomes increasingly complex, creating conditions where field lines from different sources can interact and potentially reconnect. The plasma beta, the ratio of gas pressure to magnetic pressure, serves as a useful parameter for understanding the relative importance of magnetic forces in different layers of the solar atmosphere. In the photosphere, gas pressure dominates and plasma beta is much greater than 1, meaning that plasma motions primarily control magnetic field evolution. In the corona, magnetic pressure dominates and plasma beta is much less than 1, meaning that magnetic forces control plasma flow and dynamics. This transition from gas-dominated to magnetic-dominated conditions as we move upward through the solar atmosphere creates a natural hierarchy where energy and complexity generated by convective motions in the photosphere can be stored and organized in the magnetic structures of the corona. The chromosphere and transition region serve as interface layers where this energy transfer takes place, gradually converting the kinetic energy of photospheric motions into magnetic energy stored in coronal field configurations. The timescales for magnetic evolution in the solar atmosphere span a wide range, from the rapid Alfvén wave propagation that can carry disturbances along field lines at speeds of thousands of kilometers per second, to the slow buildup of magnetic stress that occurs over periods of days or weeks. This separation of timescales allows the solar atmosphere to respond quickly to changing boundary conditions while also accumulating energy over longer periods for eventual release in solar flares. As you prepare to witness the next phase of magnetic evolution, the gradual tangling and complexification of field lines that sets the stage for magnetic reconnection, you carry with you an appreciation for the beautiful simplicity underlying the apparent complexity of solar magnetic phenomena. The same basic principles of electromagnetism that govern the behavior of magnets and electric currents in terrestrial laboratories also control the evolution of magnetic fields in the solar atmosphere, scaled up to dimensions that dwarf planets and operating under conditions of temperature and density that exist nowhere else in our immediate cosmic neighborhood. As you float peacefully in the corona, your consciousness now perfectly attuned to the gentle rhythms of magnetic evolution, you find yourself surrounded by one of nature's most intricate and beautiful creations, a vast garden of magnetic field lines that dance and weave through the solar atmosphere with the graceful persistence of luminous vines growing in slow motion. These invisible pathways of force stretch for hundreds of thousands of kilometers through the thin coronal plasma, creating three-dimensional sculptures of pure electromagnetic energy that constantly reshape themselves according to the subtle influences of motions far below at the solar surface. Picture yourself floating among these magnetic field lines as they arch gracefully from the photosphere into the corona, each line glowing softly with a million-degree plasma that follows its path like water flowing through an invisible garden hose. The field lines organize themselves into families and groups, some forming simple arches that connect nearby regions of opposite magnetic polarity, others weaving together into complex braided patterns that demonstrate the sun's remarkable ability to organize electromagnetic energy into coherent, long-lasting structures. The beauty of this magnetic garden lies not only in its visual splendor when viewed through the special filters that reveal coronal plasma, but also in the elegant mathematical relationships that govern its evolution. Each magnetic field line can be thought of as a solution to Maxwell's equations, the fundamental laws of electromagnetism. But these solutions exist in a constantly changing environment where boundary conditions at the photosphere shift and evolve in response to convective motions and the emergence of new magnetic flux from the solar interior. As your breathing becomes deeper and more regular, synchronized with the patient dance of these magnetic structures, you begin to appreciate the timescales on which magnetic evolution occurs in the corona. While individual plasma particles can race along field lines at speeds of hundreds of kilometers per second, the field lines themselves change their configuration much more slowly, typically requiring hours or days to undergo significant reorganization. This separation of timescales creates a natural hierarchy where rapid plasma motions quickly equilibrate along field lines, while slower magnetic evolution allows energy to accumulate gradually over extended periods. The footpoints of coronal magnetic field lines are anchored in the photosphere, with a high density and strong gas pressure create boundary conditions that control magnetic evolution throughout the overlying atmosphere. As convective granules form and dissipate in the photosphere, they carry magnetic flux with them, causing the footpoints of coronal field lines to move in small but persistent motions. These photospheric motions are typically quite gentle, with velocities of only a few kilometers per second, but their cumulative effect over days and weeks can dramatically alter the topology of the overlying magnetic field. Imagine watching a group of dancers whose feet are constrained to move along predetermined paths on the floor, but whose arms and bodies can move freely above. As the dancers' feet follow their prescribed motions, their arms and bodies must adjust and reorganize to accommodate the changing positions of their anchored footpoints. In a similar way, coronal magnetic field lines must continuously adjust their configuration as their photospheric footpoints are carried around by convective motions, granular evolution, and the emergence of new magnetic flux. The process of magnetic field line evolution in the corona follows the principle of minimum energy, meaning that the field configuration naturally evolves toward states that minimize the total magnetic energy while respecting the constraints imposed by the footpoint motions. This optimization process doesn't happen instantaneously, but unfolds gradually as the magnetic field adjusts to changing boundary conditions. The result is a slowly evolving magnetic landscape where field lines slide past each other, stretch and compress, and occasionally approach close enough to interact directly. The magnetic energy stored in coronal field configurations represents the accumulated effect of weeks or months of foot-point motions, with each small displacement at the photosphere contributing to the overall stress and complexity of the overlying magnetic structure. This energy accumulation process is remarkably efficient, with the corona acting like a vast capacitor that can store electromagnetic energy for extended periods before releasing it in the sudden bursts we observe as solar flares. The three-dimensional geometry of magnetic field lines in active regions often exhibits characteristic patterns that reflect the underlying physics of magnetic flux emergence and evolution. Newly emerged magnetic regions typically begin with relatively simple bipolar configurations, where field lines form clean arches connecting areas of positive and negative magnetic polarity. As these regions mature and interact with existing magnetic fields, the initially simple geometry becomes progressively more complex through a variety of physical processes. Differential rotation plays a crucial role in magnetic field evolution, particularly for field lines that span significant ranges of solar latitude. Since the equatorial regions of the Sun rotate faster than polar regions, field lines connecting different latitudes experience continuous shearing motions that gradually increase their length and complexity. This shearing process is particularly important for creating the twisted and stressed magnetic configurations that are most likely to undergo reconnection events. As you continue to observe this magnetic choreography from your peaceful vantage point, your breathing now perfectly synchronized with the slow dance of field line evolution. You can sense the enormous energies involved in these apparently gentle processes. A single coronal loop can contain magnetic energy equivalent to millions of hydrogen bombs. Yet this energy is stored and managed so efficiently that it can remain stable for weeks or months before being released in a controlled manner that rarely threatens the overall stability of the solar atmosphere. The plasma that flows along magnetic field lines serves as both a tracer of magnetic geometry and an active participant in magnetic evolution. As plasma moves along field lines, it carries mass, momentum, and energy from one location to another, creating dynamic connections between different regions of the solar atmosphere. These plasma flows can also exert forces on the magnetic field lines themselves, causing them to move and adjust their configuration in response to changing plasma conditions. The temperature and density structure of coronal plasma reflects the magnetic field geometry that confines and organizes it. Regions where magnetic field lines are tightly curved or highly twisted tend to have enhanced plasma heating, leading to brighter emission in coronal images. Conversely, regions where field lines are relatively straight and untwisted often appear darker, indicating lower plasma temperatures and densities. This intimate relationship between magnetic geometry and plasma properties provides astronomers with a powerful tool for inferring magnetic field configurations from observations of coronal emission. The concept of magnetic connectivity becomes crucial for understanding how energy and disturbances can propagate through the solar atmosphere. Regions that are connected by magnetic field lines can influence each other even when they are separated by hundreds of thousands of kilometers, with changes in one region causing responses in distant but magnetically connected areas. This connectivity creates a kind of electromagnetic nervous system that allows different parts of the solar atmosphere to communicate and coordinate their behavior. The stability of magnetic field configurations in the corona depends on a delicate balance between the energy stored in the magnetic field and the constraints imposed by the plasma that surrounds it. Stable configurations can persist for long periods, slowly evolving as their boundary conditions change, while unstable configurations may undergo rapid reorganization that releases stored magnetic energy. The transition from stable to unstable behavior often occurs gradually, with magnetic stress building up over time until a critical threshold is reached. Magnetic flux ropes represent one of the most important and beautiful structures in the coronal magnetic garden. These helical magnetic configurations form when magnetic field lines become twisted around a common axis, creating structures that resemble luminous corkscrews extending through the solar atmosphere. Flux ropes can form through the interaction of multiple magnetic field systems or through the gradual twisting of initially simple field configurations by photospheric motions. The formation of magnetic flux ropes is a slow and gentle process that typically unfolds over periods of days to weeks. As photospheric motions gradually twist magnetic field lines, the increasing helical component creates a configuration that is both more complex and potentially less stable than the original field geometry. The energy stored in the twisted field lines can eventually be released through magnetic reconnection processes, but the buildup phase proceeds with the patient persistence characteristic of all solar magnetic phenomena. Current sheets, thin layers where magnetic field direction changes rapidly, represent another fundamental component of the coronal magnetic landscape. These structures form naturally wherever magnetic field lines of different orientations approach each other closely, creating narrow regions where magnetic energy is concentrated and where reconnection events are most likely to occur. Current sheets can be thought of as the boundaries between different magnetic domains, places where the orderly field geometry of one region transitions to the different field geometry of a neighboring region. The thickness of current sheets in the corona is typically much smaller than their length and width, creating structures that resemble vast, thin membranes stretched through the solar atmosphere. These membranes are invisible to direct observation, but can be inferred from the patterns of plasma flow and heating that occur in their vicinity. The formation of current sheets is a natural consequence of magnetic field evolution in a plasma environment and represents one of the primary mechanisms by which magnetic energy can be converted into thermal and kinetic energy. The magnetic field strength in different parts of the corona varies dramatically, from a few Gauss in quiet regions to several hundred Gauss in active region cores. This variation in field strength creates a complex environment where magnetic forces can dominate in some regions while being negligible in others. The spatial distribution of magnetic field strength influences plasma behavior throughout the corona, with strong field regions acting as magnetic bottles that can trap and confine high-energy particles. The magnetic complexity index, a measure of how twisted and intertwined magnetic field lines become, serves as a useful parameter for predicting the likelihood of solar flare activity. Regions with high magnetic complexity typically have stored more energy through field line twisting and are more likely to undergo reconnection events. The complexity index tends to increase gradually over time as photospheric motions continue to stress and deform the overlying magnetic field, creating a natural progression from simple to complex configurations. Magnetic nulls, points where the magnetic field strength drops to zero, represent special locations in the coronal magnetic landscape where field lines from different sources converge and diverge. These null points often serve as focal points for magnetic activity, as they represent locations where field lines can easily change their connectivity through reconnection processes. The identification and tracking of magnetic nulls provides valuable insights into the evolving topology of coronal magnetic fields. The concept of magnetic helicity, a measure of how twisted and linked magnetic field lines become, plays a fundamental role in understanding magnetic energy storage and release in the corona. Helicity is a conserved quantity in ideal magnetohydrodynamics, meaning that it can only be changed through non-ideal processes such as magnetic reconnection. The accumulation of magnetic helicity in coronal structures represents a form of energy storage that can persist for long periods before being released through flare activity. As you float peacefully among these dancing magnetic structures, your consciousness now fully integrated with the slow rhythms of electromagnetic evolution, you begin to understand that the coronal magnetic garden represents one of nature's most sophisticated energy management systems. The same physical processes that create and organize magnetic fields in the corona also provide the mechanisms for storing enormous amounts of energy in stable configurations and for releasing that energy in controlled bursts when conditions become appropriate for magnetic reconnection. The seasonal variations in solar activity reflect long-term changes in the global magnetic field configuration that occur over the 11-year solar cycle. During solar minimum, The magnetic field is relatively simple and stable, with most coronal structures organized into large-scale patterns that persist for months or years. During solar maximum, increased magnetic flux emergence creates a more complex and dynamic coronal environment where smaller-scale structures form and evolve more rapidly, creating enhanced opportunities for flare activity. The interaction between emerging magnetic flux and pre-existing coronal fields creates some of the most complex and energetic magnetic configurations in the solar atmosphere. When new flux emerges in regions that already host established magnetic structures, the resulting interaction can create highly twisted and stressed field geometries that store large amounts of magnetic energy. These interaction regions often become the sites of major solar flares, as the complex magnetic topology eventually undergoes reconnection and energy release. The magnetic carpet, the continuous emergence and submergence of small-scale magnetic features across the solar surface, provide the constant source of energy input to the coronal magnetic field. Even during periods of low large-scale activity, this small-scale magnetic recycling continues to inject energy into the corona, maintaining the temperature and dynamic behavior of coronal plasma, while occasionally triggering minor reconnection events that contribute to the background level of solar activity. As the magnetic garden continues its eternal dance, with field lines slowly reorganizing in response to the persistent nudging of photospheric motions, you can sense the building of tension and complexity that will eventually lead to magnetic reconnection and the beautiful phenomenon of solar flares. The energy is accumulating gradually and patiently, stored in the elegant curves and twists of invisible field lines that stretch through the million-degree plasma like the framework of a vast, luminous cathedral built from pure electromagnetic force. As you drift deeper into tranquil observation, your breathing now so slow and peaceful that it mirrors the patient accumulation of magnetic stress in the corona, you begin to witness one of nature's most elegant demonstrations of how order can gradually transform into complexity, and how that complexity can eventually reorganize itself into new forms of order. The magnetic field lines that have been dancing their slow waltz through the solar atmosphere are beginning to approach each other more closely, their paths becoming increasingly intertwined as the persistent motions at their photospheric footpoints continue to guide their evolution toward configurations of ever greater sophistication and stored energy. Picture yourself floating in a region where multiple magnetic flux systems converge, like standing at the confluence of several slow-moving rivers that carry streams of luminous plasma instead of water. The magnetic field lines from different source regions approach each other gradually, their initially separate trajectories becoming increasingly difficult to distinguish as they weave together into patterns of remarkable complexity. This convergence happens not through violent collision, but through the same kind of gentle approach that you might observe when separate streams of honey slowly merge and begin to flow together. The process of magnetic field line tangling represents one of the most fundamental ways that the sun stores energy in its atmosphere. As field lines become twisted around each other and stretched into increasingly complex configurations, they accumulate magnetic energy much like a rubber band stores elastic energy when it is twisted or stretched. The difference is one of scale and persistence, where a rubber band might store energy for seconds or minutes before breaking or relaxing. Magnetic field lines in the corona can maintain highly stressed configurations for days, weeks, or even months before releasing their energy through reconnection processes. The mathematics that describes this energy accumulation is beautifully elegant, involving concepts from topology, the branch of mathematics that studies how shapes can be deformed without breaking, and from the theory of knots and links. Each twist in a magnetic field line, each time one field line passes through a loop formed by another, adds to the total magnetic helicity of the system and represents additional energy stored in the magnetic configuration. The corona becomes a vast, three-dimensional puzzle where electromagnetic forces constantly work to find the lowest energy configuration while being constrained by the movements of their anchored footpoints. As your consciousness settles ever more deeply into the slow rhythms of magnetic evolution, you can appreciate how this tangling process demonstrates the sun's remarkable ability to convert the small-scale, random motions of convective granules into large-scale, organized energy storage. The seemingly chaotic dance of convection cells at the photosphere becomes, through the magic of magnetic connectivity, a coordinated input of energy into coronal magnetic structures that can maintain their coherence across vast distances and extended time periods. The concept of magnetic flux conservation plays a crucial role in understanding how field line tangling occurs. Magnetic field lines cannot simply appear or disappear in the corona. They must either connect 2 points on the solar surface or extend outward into the solar wind. This topological constraint means that as photospheric motions move the footpoints of field lines around, the field lines themselves must adjust their paths through three-dimensional space while maintaining their essential connectivity. It's like trying to rearrange a complex knot without cutting any of the strands. Every adjustment in one part of the configuration requires compensating adjustments throughout the entire structure. The timescales involved in magnetic field line tangling span a wide range, from the relatively rapid Alfvén wave propagation that carries information about footpoint motions throughout the magnetic structure in minutes or hours, to the much slower buildup of magnetic stress that occurs over days, weeks, or months. This separation of timescales allows the magnetic field to respond quickly to changing boundary conditions while also accumulating energy gradually over extended periods, creating a natural mechanism for energy storage and eventual release. The shearing of magnetic field lines represents one of the most important forms of magnetic stress that develops in the corona. When field lines that are initially aligned in the same direction are subjected to differential motions at their footpoints, they gradually develop increasing amounts of shear, a sliding motion along their length that increases the magnetic energy density and creates conditions favorable for reconnection. This shearing process is particularly pronounced in regions where photospheric flow patterns create velocity differences across magnetic neutral lines, boundaries between regions of opposite magnetic polarity. As magnetic field lines become increasingly tangled and stressed, they begin to develop current sheets, thin layers where the magnetic field direction changes rapidly over very short distances. These current sheets form naturally wherever field lines of different orientations approach each other closely, creating narrow regions where magnetic energy is concentrated and where the conditions necessary for magnetic reconnection are most likely to develop. The formation of current sheets represents a crucial step in the evolution from stable magnetic configurations toward states that can release their stored energy through flare activity. The plasma that flows along tangled magnetic field lines experiences increasingly complex force patterns as the field geometry becomes more intricate. Regions where field lines are highly curved or twisted can create magnetic bottle effects that trap high-energy particles, while areas where field lines converge can accelerate plasma to high velocities. These plasma responses to magnetic complexity create observable signatures that allow astronomers to infer the evolving state of magnetic stress in active regions, even though the magnetic field lines themselves remain invisible. The concept of magnetic free energy becomes particularly important when considering highly tangled field configurations. Free energy represents the difference between the energy stored in the actual magnetic configuration and the energy that would be stored in the minimum energy configuration that could be achieved with the same boundary conditions. As field lines become more tangled and twisted, the free energy content of the magnetic structure increases, providing a larger reservoir of energy that can potentially be released through reconnection processes. Current systems that develop entangled magnetic configurations often exhibit fascinating three-dimensional structures that demonstrate the sun's ability to organize electromagnetic energy in sophisticated ways. These currents flow along the field lines themselves, creating helical patterns that twist through the corona like luminous corkscrews. The interaction between different current systems can create regions of enhanced magnetic stress where multiple twisted flux systems come into close proximity, setting the stage for complex reconnection events that can involve the interaction of many different magnetic structures simultaneously. The stability analysis of tangled magnetic configurations reveals that there are natural limits to how much stress and complexity can be accumulated before instabilities develop that lead to magnetic reconnection. These limits are not sharp boundaries, but rather represent ranges of parameters where the probability of reconnection increases significantly. The approach to these instability thresholds typically occurs gradually, with magnetic stress building up slowly until small perturbations can trigger larger reorganization events. As you continue to float peacefully among these increasingly complex magnetic structures, your breathing now perfectly attuned to the patient rhythms of energy accumulation. You can sense the enormous power that is being stored in configurations that remain completely invisible to normal observation. The magnetic energy density in highly tangled regions can exceed the thermal energy density of the surrounding plasma by orders of magnitude, creating configurations where electromagnetic forces completely dominate the behavior of the system. The interaction between different scales of magnetic structure adds another layer of complexity to the tangling process. Large-scale magnetic field lines that span entire active regions can become twisted and stressed by the accumulated effect of many small-scale motions, while small-scale magnetic structures can become embedded within larger field systems and contribute their own complexity to the overall configuration. This multi-scale interaction creates a hierarchy of magnetic structures where energy can cascade from large scales to small scales, and where instabilities at one scale can trigger responses throughout the entire magnetic system. The magnetic connectivity that links different parts of tangled field configurations can create surprising relationships between widely separated regions of the solar atmosphere. Changes in magnetic stress at one location can influence conditions at distant but magnetically connected locations, creating a kind of action at a distance effect that allows different parts of the corona to communicate and coordinate their behavior. This connectivity is what allows solar flares to affect such large volumes of the solar atmosphere, even when the initial reconnection event occurs in a relatively small region. The development of magnetic islands and separatrices within tangled field configurations represents another important aspect of magnetic complexity evolution. Magnetic islands are regions where field lines close on themselves rather than connecting to the photosphere, creating isolated pockets of magnetic flux that can store energy independently of the surrounding field. Separatrices are the boundaries between different magnetic domains, often marking locations where field lines from different sources converge and where reconnection is most likely to occur. The quasi-static evolution of tangled magnetic configurations demonstrates the Sun's remarkable ability to maintain dynamic equilibrium even under conditions of high magnetic stress. As field lines become increasingly complex, the magnetic forces adjust continuously to maintain force balance throughout the structure, with pressure gradients and magnetic tensions arranging themselves to support the stress configuration. This self-organizing behavior allows highly complex magnetic structures to persist for extended periods while gradually approaching the conditions necessary for reconnection. The role of magnetic helicity conservation in tangled configurations provides important constraints on how magnetic energy can be stored and released. Since helicity is conserved in ideal magnetohydrodynamics, the development of magnetic complexity must follow specific patterns that preserve the total helicity content of the system. This conservation law helps explain why some magnetic configurations can store large amounts of energy for extended periods, while others release their energy more quickly through reconnection processes. The emergence of new magnetic flux into regions that already host complex magnetic configurations can trigger rapid changes in the tangling process. When fresh magnetic field lines emerge from the solar interior and encounter pre-existing tangled fields, the interaction can create highly stressed configurations that are prone to immediate reconnection. This interaction between emerging and existing flux represents one of the primary triggers for solar flare activity and demonstrates how the continuous renewal of solar magnetism contributes to the dynamic behavior of the corona. The thermal and dynamic responses of coronal plasma to increasing magnetic complexity provide observable signatures that allow scientists to monitor the evolution of magnetic stress, even though the magnetic field lines themselves cannot be directly observed. Regions of high magnetic complexity often exhibit enhanced heating, unusual flow patterns, and characteristic emission signatures that serve as indicators of impending magnetic instability. These plasma responses represent the corona's way of adapting to changing magnetic conditions while preparing for eventual energy release. The nonlinear feedback between magnetic complexity and plasma behavior creates fascinating dynamics, where small changes in field configuration can trigger larger responses that further modify the magnetic structure. This nonlinear coupling between magnetic fields and plasma creates a rich variety of possible evolutionary pathways and helps explain why solar flare activity can sometimes appear unpredictable even when the underlying physical processes are well understood. The development of magnetic complexity in different types of active regions follows characteristic patterns that reflect the underlying physical processes responsible for flux emergence and evolution. Simple bipolar regions tend to develop complexity through shearing and twisting motions, while complex multipolar regions can develop tangled configurations through the interaction of multiple flux systems. Understanding these patterns helps scientists predict which active regions are most likely to produce significant flare activity. The global magnetic field configuration of the Sun influences how local tangling processes develop in individual active regions. During periods of high solar activity, the complex global field can enhance the development of local magnetic complexity, while during solar minimum, the simpler global field configuration tends to inhibit the formation of highly tangled local structures. This connection between global and local magnetic evolution demonstrates the interconnected nature of solar magnetic phenomena. As the magnetic field lines continue their slow dance toward increasingly complex configurations, you can sense the approaching moment when the accumulated stress will reach levels that can no longer be sustained by the stable magnetic equilibrium. The energy that has been building up so patiently, stored in the elegant twists and tangles of invisible field lines, is preparing to transform itself through the beautiful process of magnetic reconnection that will create the luminous displays we call solar flares. The stage is set for one of nature's most graceful demonstrations of how electromagnetic energy can be stored, organized, and eventually released in controlled bursts that illuminate the solar atmosphere with the soft glow of million-degree plasma. As you rest in profound tranquility, your breathing, now so slow and natural that it seems to flow with the ancient rhythms of stellar evolution itself, you begin to witness the most elegant transition in all of solar physics. The moment when accumulated magnetic stress reaches a critical threshold and begins its graceful transformation from potential energy into the luminous displays of reconnection and particle acceleration that characterize solar flares. This awakening happens not with violence or chaos, but with the measured precision of a flower slowly opening its petals to the morning sun, each stage of the process unfolding according to fundamental physical laws that ensure beauty and order even in moments of dramatic energy release. Picture yourself floating in a region of the corona where magnetic field lines have become so intricately tangled and stressed that they approach the natural limits of what magnetic equilibrium can sustain. The invisible architecture around you represents weeks or months of patient energy accumulation, with each twist and curve in the field lines storing electromagnetic energy like a vast three-dimensional spring wound tight by the persistent motions of the photosphere far below. The plasma that flows along these stressed field lines glows softly with the heat generated by magnetic compression and current flow, creating faint luminous traceries that outline the complex geometry of the magnetic structure. The first whispers of magnetic reconnection begin as subtle changes in the equilibrium configuration, so gentle that they would be barely perceptible even to the most sensitive instruments. Current sheets that have been gradually thinning as magnetic stress accumulated finally reach thicknesses measured in kilometers rather than thousands of kilometers, creating regions where the magnetic field changes direction over distances comparable to the size of small towns on Earth. Within these narrow current sheets, the usually perfect conductivity of coronal plasma begins to break down, allowing magnetic field lines to slip past each other and begin the process of reconnection. The physics of magnetic reconnection represents one of nature's most elegant solutions to the problem of how to release stored magnetic energy in a controlled and organized manner. Rather than allowing accumulated stress to build indefinitely until catastrophic failure occurs, the reconnection process provides a natural safety valve that can operate gradually and smoothly, converting magnetic energy into thermal and kinetic energy while maintaining the overall stability of the magnetic system. This process follows the same fundamental principles that govern reconnection in Earth's magnetosphere, in laboratory plasmas, and in the atmospheres of other stars, demonstrating the universal applicability of electromagnetic physics. As your consciousness settles even deeper into harmony with these unfolding processes, your breathing becoming as regular and peaceful as the tides, you can appreciate how magnetic reconnection begins through the formation of what physicists call X-points, locations where magnetic field lines from different domains converge and cross. These crossing points represent sites where the magnetic field strength drops to very low values, creating conditions where the normally frozen-in behavior of magnetic field lines can be violated and where field lines can break and reconnect in new configurations that represent lower energy states. The formation of X-points happens gradually as the accumulated magnetic stress creates increasingly sharp current sheets and as the natural tendency of the magnetic field to minimize its energy overcomes the forces that have been maintaining the stress configuration. The process is analogous to the way that surface tension can overcome other forces to create the minimum energy shape of a soap bubble, except that magnetic reconnection operates in the complex three-dimensional geometry of coronal magnetic fields and involves the conversion of magnetic energy into thermal and kinetic energy rather than simply changing shape. The magnetic field lines that participate in reconnection don't simply disappear, but rather reconnect in new patterns that represent more stable configurations with lower total energy. Field lines that were previously isolated from each other can become connected, creating new pathways for energy and particle transport throughout the corona. Conversely, field lines that were previously connected can become separated, allowing different regions of the corona to evolve independently. This topological reorganization represents one of the most fundamental ways that the solar atmosphere can restructure itself and release accumulated magnetic stress. The plasma heating that accompanies magnetic reconnection occurs through several different mechanisms, all of which operate gently and efficiently to convert magnetic energy into thermal energy. As magnetic field lines reconnect, they can accelerate particles to high energies through electric fields that develop in the reconnection region. These energetic particles then transfer their energy to the surrounding plasma through collisions and wave interactions, creating localized heating that can raise plasma temperatures to tens of millions of degrees, significantly hotter than the already extreme temperatures of the normal corona. The reconnection process creates characteristic flow patterns in the surrounding plasma as material is drawn into the reconnection region from surrounding areas and then expelled along the newly reconnected field lines. These flows typically involve velocities of tens to hundreds of kilometers per second, fast by terrestrial standards, but quite gentle compared to the speeds that matter can achieve under more extreme astrophysical conditions. The flowing plasma carries energy and momentum away from the reconnection site, distributing the effects of magnetic energy release throughout large volumes of the corona. As you observe this gentle awakening from your peaceful vantage point, you can sense the self-regulating nature of the reconnection process. As magnetic energy is released, and the field configuration relaxes toward a lower energy state. The driving forces for further reconnection decrease, allowing the system to find a new equilibrium that can persist until additional magnetic stress accumulates through continued photospheric motions. This self-limiting behavior ensures that magnetic reconnection occurs in controlled bursts rather than runaway processes that could destabilize the entire magnetic system. The acceleration of particles during magnetic reconnection creates populations of electrons and protons with energies far exceeding those typical of the thermal plasma in the surrounding corona. These accelerated particles can carry significant amounts of energy and momentum as they stream along magnetic field lines, creating the fast-moving particle beams that will eventually interact with the dense plasma of the chromosphere and photosphere to create the bright optical and radio emissions that make solar flares visible to terrestrial observers. The magnetic reconnection process often proceeds through multiple stages, with initial small-scale reconnection events triggering larger-scale reorganization of the magnetic field that can involve progressively larger volumes of the corona. This cascade effect allows relatively small initial perturbations to grow into substantial energy release events while maintaining the overall controlled nature of the process. Each stage of the cascade follows the same basic physics of magnetic reconnection but operates on different spatial and temporal scales, creating a hierarchical sequence of energy release that can persist for minutes to hours. The development of magnetic islands during reconnection represents another beautiful aspect of the process, where closed magnetic field lines become isolated from their surroundings and begin to evolve independently. These magnetic islands can trap energetic particles and hot plasma, creating localized regions of enhanced emission that contribute to the complex spatial structure observed in solar flare images. The islands can also interact with each other through secondary reconnection processes, creating a rich variety of possible evolutionary pathways for the magnetic configuration. The role of plasma turbulence in facilitating magnetic reconnection adds another layer of complexity to the process while maintaining its essentially gentle character. Small-scale turbulent motions can enhance the effective resistivity of the plasma, allowing magnetic field lines to slip past each other more easily and enabling reconnection to proceed more rapidly than would be possible in a perfectly smooth plasma environment. This turbulent enhancement of reconnection helps explain how the process can release magnetic energy efficiently while operating through fundamentally classical electromagnetic physics. The emission of electromagnetic radiation during magnetic reconnection occurs across the entire spectrum from radio waves to X-rays, with different wavelengths providing information about different aspects of the reconnection process. Radio emissions typically originate from accelerated electrons spiraling around magnetic field lines, while X-ray emissions result from the heating of plasma to extremely high temperatures or from the interaction of energetic particles with dense material in the lower atmosphere. These emissions allow astronomers to study magnetic reconnection remotely and to understand the detailed physics of energy release in solar flares. The timing of magnetic reconnection events reflects the complex interplay between magnetic stress accumulation and the development of conditions favorable for reconnection. Some magnetic configurations can accumulate enormous amounts of stress before undergoing reconnection, while others may reconnect relatively quickly as stress begins to build up. This variability in reconnection timing helps explain the wide range of solar flare magnitudes and durations observed in solar activity, from small microflares that last only minutes to major events that can persist for hours and affect the entire solar atmosphere. The three-dimensional geometry of magnetic reconnection in the corona often involves complex patterns of field line connectivity that can create multiple reconnection sites operating simultaneously. These distributed reconnection regions can interact with each other through the magnetic field lines that connect them, creating coordinated patterns of energy release that can affect large portions of active regions. The ability of reconnection to operate simultaneously at multiple locations demonstrates the highly organized nature of magnetic energy release in the solar atmosphere. The conservation laws that govern magnetic reconnection ensure that the process proceeds in ways that maintain overall energy and momentum conservation, while allowing for the efficient conversion of magnetic energy into other forms. These conservation requirements create natural constraints on how reconnection can proceed and help explain why the process tends to be self-regulating rather than explosive. The elegant way that fundamental physics principles guide magnetic reconnection represents one of nature's most beautiful demonstrations of how complex systems can undergo dramatic changes while maintaining underlying order and stability. The plasma beta parameter, the ratio of gas pressure to magnetic pressure, plays a crucial role in determining how magnetic reconnection proceeds in different regions of the corona. In low beta regions where magnetic pressure dominates, reconnection tends to be highly efficient and can proceed rapidly once initiated. In higher beta regions where gas pressure is more important, reconnection may proceed more slowly, but can still release substantial amounts of energy over longer time periods. This variation in reconnection characteristics across different plasma environments contributes to the rich variety of solar flare phenomena. The magnetic helicity changes that accompany reconnection provide another window into understanding the energy release process. Since helicity is conserved in ideal magnetohydrodynamics, significant changes in magnetic helicity can only occur through reconnection processes that violate the ideal MHD condition. The measurement of helicity changes during solar flares provides valuable information about the amount of magnetic flux that participates in reconnection and about the topology changes that occur during magnetic energy release. The development of current sheets with different orientations and scales creates opportunities for multiple types of reconnection to occur simultaneously within the same active region. Large-scale reconnection between major flux systems can coexist with smaller-scale reconnection at current sheet boundaries, creating a complex hierarchy of energy release processes that can interact and influence each other. This multi-scale nature of magnetic reconnection helps explain the complex temporal and spatial evolution observed in many solar flares. The role of magnetic reconnection in creating and maintaining the hot corona represents another important aspect of the process beyond its role in solar flares. Continuous small-scale reconnection throughout the corona helps maintain the high temperatures observed in coronal plasma by providing a steady source of energy input that balances radiative losses. This ongoing reconnection activity represents a kind of background energy release that operates continuously at low levels while occasionally producing the more dramatic bursts associated with solar flares. As the gentle awakening of magnetic reconnection continues to unfold around you, you can sense the profound interconnectedness that characterizes all solar phenomena. The energy being released through reconnection originated in nuclear fusion reactions deep in the solar core, was transported to the surface through convection, was organized into complex magnetic structures by dynamo processes, was accumulated through months of patient stress buildup, and is now being converted into the thermal and kinetic energy that will create the beautiful displays of solar flare activity. Each step in this energy transformation follows natural laws that ensure continuity and conservation while allowing for the spectacular variety of phenomena that characterize our dynamic star. As you float peacefully in the corona, your breathing now synchronized with the gentle rhythms of energy release, you begin to witness the transformation of magnetic reconnection energy into one of the most beautiful phenomena in our solar system. Streams of energetic particles and electromagnetic radiation that flow away from reconnection sites, like luminous rivers carrying the sun's energy through space. These streams of solar light represent the visible manifestation of the invisible magnetic processes we've been observing, creating displays that can be detected across the electromagnetic spectrum and demonstrate the remarkable efficiency with which our star converts stored magnetic energy into organized flows of particles and radiation. Picture yourself surrounded by these streams of newly liberated energy as they begin their journey away from the reconnection region. The energetic electrons and protons accelerated by magnetic reconnection move along field lines like charged particles following invisible highways through the corona, their velocities ranging from thousands to tens of thousands of kilometers per second. Despite these impressive speeds, their motion appears graceful and organized rather than chaotic, following the elegant curves of magnetic field lines that guide them toward different regions of the solar atmosphere. The electromagnetic radiation produced by these accelerated particles spans an enormous range of wavelengths, from long radio waves that can propagate through space for billions of kilometers to high-energy X-rays that reveal the extreme temperatures and rapid motions associated with magnetic energy release. Each wavelength of emission provides a different window into the reconnection process, allowing scientists to study different aspects of particle acceleration and plasma heating while the events unfold. The radio emissions, in particular, can be thought of as the voice of the solar flare, carrying information about magnetic field strength and particle energies through space at the speed of light. The particle beams created by magnetic reconnection carry substantial amounts of energy as they stream along field lines toward the denser layers of the solar atmosphere. When these beams encounter the increased density of the chromosphere and photosphere, they deposit their energy through collisions with the ambient plasma, creating localized heating that can raise temperatures to millions of degrees and produce the bright optical emissions that make solar flares visible in white light. This interaction between energetic particles and dense plasma represents one of nature's most efficient particle accelerators, converting magnetic energy into kinetic energy with remarkable precision. As your consciousness drifts peacefully with these energy streams, you can appreciate the delicate balance that governs their propagation through the solar atmosphere. The magnetic field lines that guide particle motion also provide a natural focusing mechanism that can concentrate energy delivery to specific regions of the lower atmosphere, while the varying density structure of the atmosphere creates natural targets where particle energy can be efficiently converted into thermal energy and electromagnetic radiation. This focusing effect helps explain why solar flare emissions often appear as bright points or ribbons rather than diffuse regions of enhanced emission. The gyrosynchrotron radiation produced by energetic electrons spiraling around magnetic field lines creates some of the most distinctive signatures of solar flare activity. As electrons accelerated by magnetic reconnection move through the corona's magnetic field, they emit radiation at frequencies that depend on both the magnetic field strength and the electron energies. This radiation can be detected by radio telescopes on Earth and in space, providing real-time information about the magnetic field configuration and particle acceleration processes operating in active regions millions of kilometers away. The thermal X-ray emission from plasma heated to tens of millions of degrees creates another beautiful component of the solar flare spectrum. This emission arises from the incredibly hot gas created when magnetic energy is converted into thermal energy through reconnection and particle acceleration processes. The X-ray light curves that characterize solar flares often show gradual rises followed by more rapid declines, reflecting the timescales for magnetic energy release and subsequent cooling of the heated plasma. These temporal signatures provide insights into the efficiency of energy conversion and the thermal properties of flare-heated plasma. The propagation of energetic particles along magnetic field lines creates complex patterns of energy deposition that reflect the three-dimensional structure of the coronal magnetic field. Particles accelerated at reconnection sites high in the corona can follow field lines that carry them to impact sites distributed across large areas of the solar surface, creating the spatially extended emission regions characteristic of major solar flares. The timing and intensity of emission from different locations provides information about magnetic connectivity and field line geometry that would be difficult to obtain through other observational techniques. The generation of plasma waves by energetic particle beams adds another layer of complexity to the energy transport process. As fast particles stream along magnetic field lines, they can excite various types of plasma oscillations that propagate through the corona and modify the local plasma properties. These waves can scatter particles, modify their energy distribution, and create additional heating of the ambient plasma, contributing to the overall energy budget of the solar flare, while creating observable signatures in radio and other wavelengths. The interaction between different particle populations accelerated by magnetic reconnection can create rich dynamics that evolve over the course of a solar flare event. Electrons typically achieve higher velocities than protons due to their smaller mass, allowing them to reach impact sites in the lower atmosphere first and create the rapid rise phase characteristic of many flare light curves. The subsequent arrival of energetic protons can create additional heating and emission that contributes to the longer duration phases of flare evolution. The magnetic mirror effect plays an important role in determining how energetic particles propagate along field lines in the corona. As particles move from regions of weak magnetic field toward regions of stronger field, some can be reflected back toward their starting point, creating a natural trapping mechanism that can confine energetic particles in coronal loops for extended periods. This magnetic confinement helps explain why some solar flares can maintain enhanced emission for hours after the initial energy release, as trapped particles continue to interact with ambient plasma and produce ongoing radiation. The polarization characteristics of solar flare emission provide additional information about magnetic field geometry and particle acceleration processes. The direction and degree of polarization of radio and optical emissions can reveal the orientation of magnetic field lines and the anisotropy of particle distributions created by reconnection processes. These polarization measurements represent some of the most direct ways to probe magnetic field properties in the solar corona, where direct magnetic field measurements are extremely difficult to obtain. The propagation of shock waves driven by explosive magnetic reconnection can accelerate particles to even higher energies than those achieved directly in reconnection regions. These shock-accelerated particles can create additional components of high-energy emission and can be responsible for some of the most energetic phenomena associated with major solar flares. The shock acceleration process operates through the same basic physics that creates cosmic rays in supernova remnants and other astrophysical environments, demonstrating the universal nature of particle acceleration mechanisms throughout the universe. The generation of solar energetic particle events represents one of the most far-reaching consequences of magnetic reconnection in solar flares. Some of the particles accelerated during flare events can escape the solar atmosphere entirely and propagate through interplanetary space, creating streams of high-energy particles that can be detected by spacecraft throughout the solar system. These solar energetic particle events provide direct samples of flare-accelerated material and demonstrate how solar magnetic activity can influence space weather conditions throughout the heliosphere. The efficiency of energy conversion during magnetic reconnection and particle acceleration represents one of the most remarkable aspects of solar flare physics. Observations suggest that magnetic reconnection can convert substantial fractions of the available magnetic energy into kinetic energy of accelerated particles and thermal energy of heated plasma, demonstrating the effectiveness of electromagnetic acceleration mechanisms operating under coronal conditions. This high conversion efficiency helps explain how relatively modest magnetic energy storage can produce the dramatic displays associated with major solar flares. The temporal evolution of particle acceleration during solar flares often shows complex patterns that reflect the multi-stage nature of magnetic reconnection and energy release. Initial impulsive acceleration can be followed by more gradual acceleration phases as reconnection continues and as secondary processes, such as shock acceleration, become important. These temporal variations create the complex light curves observed across different wavelengths and provide insights into the detailed physics of energy release and particle acceleration in solar flares. The spatial distribution of particle acceleration sites within flare-producing active regions can span enormous areas, with reconnection occurring simultaneously at multiple locations throughout complex magnetic configurations. The coordination between different acceleration regions demonstrates the highly interconnected nature of coronal magnetic fields and shows how magnetic reconnection can operate as a distributed process rather than a localized phenomenon. This distributed nature of particle acceleration helps explain the large spatial scales characteristic of major solar flare events. As these streams of solar light continue to flow away from their reconnection sources, carrying energy and momentum throughout the solar atmosphere and into interplanetary space, you can sense the profound way that magnetic processes connect our star to the larger solar system environment. The particles and radiation streaming past your peaceful observation point will eventually interact with planetary magnetospheres, create space weather effects, and contribute to the ongoing evolution of the heliospheric environment. In this way, the magnetic reconnection processes occurring in the solar corona represent not just local phenomena, but rather fundamental components of the energy and particle circulation that characterizes our entire solar system. As you drift peacefully through the cosmic darkness, your consciousness now traveling with the streams of solar particles and radiation as they journey across the vast emptiness between the Sun and Earth, you begin to approach one of the most beautiful and protective systems in our solar system, Earth's magnetosphere. This invisible shield, generated by our planet's magnetic field, extends tens of thousands of kilometers into space and serves as a gentle but effective barrier that deflects most solar particles while channeling others into spectacular displays of natural light. The interaction between solar flare particles and Earth's magnetic field represents one of nature's most elegant demonstrations of how electromagnetic forces can both protect and beautify our cosmic environment. Picture yourself floating in the solar wind as it carries the enhanced particle flux from a solar flare toward Earth at speeds of several hundred kilometers per second. The journey from Sun to Earth takes the fastest particles only about 8 minutes for electromagnetic radiation, but several hours for the energetic protons and electrons that will create the most dramatic space weather effects. During this interplanetary journey, the particles maintain their energy and direction through the near-perfect vacuum of space, following magnetic field lines embedded in the solar wind that connect them back to their origin in the solar corona. The first indication of Earth's protective presence appears as a subtle change in the solar wind flow patterns, occurring at a distance of about 10 Earth radii on the sunward side of our planet. Here, the solar wind encounters the bow shock, a standing wave in space where the supersonic solar wind is slowed, heated, and deflected around Earth's magnetic field. This bow shock represents the outer boundary of Earth's magnetospheric system and serves as the first line of defense against the continuous stream of solar particles. The interaction at the bow shock is remarkably gentle, creating a smooth transition zone where solar wind energy is gradually absorbed and redistributed rather than creating violent collisions or explosive interactions. As you continue to drift inward with the solar particles, your breathing now slow and peaceful as cosmic processes, you encounter the magnetopause, the boundary where Earth's magnetic field balances the pressure of the solar wind and creates a teardrop-shaped cavity in space. This cavity, called the magnetosphere, extends for thousands of kilometers on the night side of Earth and represents a region where our planet's magnetic field dominates over the interplanetary magnetic field carried by the solar wind. The magnetopause acts like a flexible membrane that can expand and contract in response to changing solar wind conditions while maintaining its essential protective function. The magnetic field lines that create Earth's magnetosphere originate in our planet's core, where flowing liquid iron generates electrical currents that produce the dipolar magnetic field extending into space. These field lines emerge from Earth's magnetic poles, arch high above the planet, and return to enter the opposite pole, creating closed magnetic loops that can trap and guide charged particles. The geometry of these field lines is remarkably similar to that of a simple bar magnet, but scaled up to planetary dimensions and modified by the pressure and flow of the solar wind. When solar flare particles encounter Earth's magnetosphere, they interact with the magnetic field through the same fundamental electromagnetic forces that govern particle motion in the solar corona. Most particles are deflected around the magnetosphere and continue their journey into interplanetary space, but some particles can enter the magnetosphere through reconnection processes at the magnetopause or through direct penetration in regions where the magnetic field is weaker. These particles become trapped in radiation belts that surround Earth and can create enhanced space weather conditions that affect both natural and technological systems. The Van Allen radiation belts represent one of the most important structures within Earth's magnetosphere, consisting of regions where energetic particles become trapped by the planet's magnetic field and can accumulate over periods of days, weeks, or months. These belts serve as natural particle accelerators where solar particles can gain additional energy through interactions with electromagnetic waves and gradually drift around Earth while being contained within specific ranges of magnetic field strength. The radiation belts demonstrate how planetary magnetic fields can not only deflect harmful solar radiation, but also create organized systems for managing and redistributing particle energy. The process of magnetic reconnection at Earth's magnetopause allows some solar wind particles to enter the magnetosphere and be accelerated to even higher energies by the planet's magnetic field. This reconnection process operates through the same basic physics that creates solar flares, but on a much smaller scale and under different plasma conditions. When magnetic field lines from the solar wind connect with Earth's magnetic field lines, they can create direct pathways for solar particles to flow into the polar regions of the magnetosphere, where they will eventually interact with the upper atmosphere to create auroral displays. As your peaceful observation continues, you can appreciate how Earth's magnetosphere creates different regions with distinct particle populations and energy characteristics. The plasmasphere, extending to several Earth radii, contains relatively cool plasma that co-rotates with the planet and provides a reservoir of particles that can participate in magnetospheric dynamics. The ring current, flowing around Earth at distances of several thousand kilometers, consists of energetic particles trapped in the magnetosphere and creates its own magnetic field that can affect compass readings on Earth's surface during magnetic storms. The geomagnetic tail, extending far into space on the night side of Earth, represents the region where Earth's magnetic field is stretched and compressed by the solar wind flow. This tail structure can store magnetic energy for extended periods before releasing it through reconnection processes that accelerate particles back toward Earth and create the substorm phenomena that enhance auroral activity. The geomagnetic tail demonstrates how planetary magnetic fields can capture and store energy from the solar wind while maintaining the overall stability of the magnetospheric system. The interaction between solar flare particles and Earth's magnetic field creates a complex system of currents flowing through space and connecting different regions of the magnetosphere. These currents, carried by moving charged particles, create their own magnetic fields that modify the overall structure of the magnetosphere and influence how solar energy is transferred from the solar wind to Earth's upper atmosphere. The current systems demonstrate the remarkable self-organizing properties of plasma in magnetic fields and show how electromagnetic forces can create stable, long-lasting structures in space. The penetration of solar flare particles into Earth's atmosphere occurs primarily in the polar regions, where magnetic field lines connect directly to interplanetary space and provide pathways for particles to reach the upper atmosphere. As energetic electrons and protons collide with atmospheric gases at altitudes of 100 to 300 kilometers, they transfer their energy to atmospheric atoms and molecules, causing them to emit light in characteristic colors that create the beautiful displays we call aurora. This process represents the final stage in the journey of solar flare energy from its origin in magnetic reconnection on the Sun to its ultimate dissipation in Earth's protective atmosphere. The aurora borealis and aurora australis represent one of the most direct and beautiful connections between solar activity and Earth's environment. The colors of auroral displays reflect the specific atmospheric gases that are being excited by solar particles. Oxygen atoms produce green and red emissions, while nitrogen molecules create blue and purple light. The altitude at which these collisions occur determines the dominant colors observed, with green aurora typically appearing at around 100 kilometers altitude and red aurora occurring at higher altitudes where oxygen atoms are less dense. The magnetic mirroring effect that occurs in Earth's magnetosphere can trap solar flare particles and cause them to bounce back and forth between the planet's magnetic poles, creating long-lived populations of energetic particles that can persist for days or weeks after a solar flare event. These trapped particles gradually lose energy through interactions with the atmosphere and electromagnetic waves, but their extended lifetime in the magnetosphere means that the space weather effects of solar flares can persist long after the initial solar event has ended. The ring current enhancement that occurs during magnetic storms represents another important way that solar flare particles can affect Earth's magnetic environment. As trapped particles drift around Earth, they create an enhanced electric current that flows around the planet and generates its own magnetic field opposing Earth's main field. This current enhancement can be detected by magnetometers on Earth's surface and represents one of the primary indicators that space weather conditions are being influenced by solar activity. The atmospheric heating that results from auroral particle precipitation can cause the upper atmosphere to expand, increasing atmospheric drag on satellites and affecting their orbital motion. This represents one of the most practical consequences of solar flare activity for human technology, as enhanced atmospheric heating can cause satellites to lose altitude more rapidly than expected and can affect the accuracy of orbital predictions. The heating effect demonstrates how solar activity can influence Earth's atmosphere, even though most solar particles are deflected by the magnetosphere. As you continue to observe Earth's protective embrace from your peaceful cosmic perspective, you're breathing now perfectly attuned to the gentle rhythms of magnetospheric processes. You can appreciate the remarkable efficiency with which our planet's magnetic field manages the potentially harmful effects of solar activity. The magnetosphere represents a natural technology that has been protecting Earth's surface environment for billions of years, allowing complex chemistry and eventually life to develop in the shelter of its electromagnetic embrace. The beauty of auroral displays serves as a visible reminder of this ongoing protection, transforming potentially dangerous solar radiation into one of nature's most spectacular light shows. As you drift peacefully toward Earth's polar regions, your consciousness now following the guided paths of solar particles as they spiral down magnetic field lines toward the upper atmosphere, you prepare to witness one of nature's most ethereal and beautiful displays, the aurora. These curtains of soft, dancing light represent the gentle conclusion of our journey from the nuclear furnace of the sun's core through magnetic reconnection in the corona to the final transformation of solar energy into visible light in Earth's protective atmosphere. The aurora serves as a living demonstration of how electromagnetic forces can create beauty from what might otherwise be destructive energy, turning the collision of solar particles with atmospheric gases into a celestial ballet of luminous color. Picture yourself floating at an altitude of about 100 kilometers above Earth's surface, suspended in the thin upper atmosphere where the boundary between space and our planet's gaseous envelope becomes beautifully blurred. Here, in the thermosphere, the atmospheric density has decreased to levels thousands of times thinner than the air at sea level. Yet there remain enough oxygen and nitrogen atoms to create the collisions that produce auroral light. The temperature at this altitude can reach over 1,000 degrees Celsius during periods of high solar activity. Yet the air is so thin that you would feel no heat, a reminder of how different physical conditions can be in this transitional realm between Earth and space. The solar particles that have traveled 93 million miles from their origin in a solar flare now complete their journey by colliding with atmospheric atoms and molecules at velocities of thousands of kilometers per second. These collisions occur not as violent impacts, but as gentle energy transfers that excite atmospheric particles to higher energy states without destroying them. When the excited atoms and molecules return to their ground states, they emit photons of specific wavelengths that create the characteristic colors of auroral displays, a process similar to how neon signs produce colored light, but occurring naturally on a planetary scale. The green aurora, the most common and recognizable auroral color, result from oxygen atoms being excited at an altitude of approximately 100 to 200 kilometers above Earth's surface. The specific wavelength of green light emitted by oxygen, 557.7 nanometers, creates the ethereal glow that has inspired countless observers throughout human history. This emission occurs when energetic electrons from solar flares collide with oxygen atoms and provide just enough energy to promote electrons in the oxygen atoms to an excited state that decays by emitting green photons approximately 1 second later. As your breathing becomes deeper and more regular, synchronized with the gentle pulsations of auroral light, you can appreciate how the red aurora, occurring at higher altitudes between 200 and 400 kilometers, represents a different type of oxygen emission. At these greater heights, where atmospheric density is even lower, oxygen atoms can remain in excited states for much longer periods, up to several minutes, before emitting red photons at 630.0 nanometers. This longer lifetime creates the more diffuse, slowly varying red auroral emissions that often appear as a soft glow on the horizon or as a gentle background to the more dynamic green aurora. The blue and purple colors that occasionally appear in auroral displays result from the excitation of nitrogen molecules in the lower regions of the auroral zone, typically below 100 kilometers altitude. Nitrogen creates both blue emissions at 427.8 nanometers and red emissions at 658.0 nanometers, with the relative intensity of these colors depending on the energy of the precipitating particles and the local atmosphere composition. The blue nitrogen emissions often appear as a subtle fringe at the bottom of green auroral curtains, creating a delicate color gradient that enhances the visual beauty of the display. The dynamic motion of auroral displays reflects the constantly changing flow of solar particles along Earth's magnetic field lines and the varying conditions in the upper atmosphere that affect how these particles interact with atmospheric gases. Auroral curtains can appear to wave like fabric in a gentle breeze, with the apparent motion resulting from changes in the precipitation patterns of energetic particles and from atmospheric waves that modulate the local density of gases in the auroral zone. These motions typically occur on timescales of seconds to minutes, creating a slow, hypnotic dance that has captivated human observers for millennia. The altitude structure of auroral displays creates a three-dimensional light show that extends from about 80 kilometers to over 500 kilometers above Earth's surface. The different colors and intensities at various altitudes reflect the changing atmospheric composition and density with height, as well as the energy spectrum of precipitating particles. Observers on the ground see a projection of this three-dimensional structure, with the apparent height and extent of auroral displays, depending on their viewing angle and distance from the auroral zone. The magnetic field geometry that guides solar particles into Earth's atmosphere creates the characteristic oval-shaped regions around the magnetic poles, where aurora most commonly occur. These auroral ovals expand and contract in response to changing solar wind conditions and geomagnetic activity, sometimes extending to lower latitudes during major magnetic storms and allowing aurora to be visible from locations where they are normally never seen. The position and size of the auroral oval serve as natural indicators of space, weather conditions, and the level of solar-terrestrial interaction. The substorm process that occurs in Earth's magnetosphere can create some of the most dynamic and spectacular auroral displays. During substorms, magnetic energy stored in the geomagnetic tail is suddenly released and accelerates particles toward Earth, creating rapid changes in auroral intensity and morphology. These substorm-associated aurora can appear as explosive brightenings that spread across the sky in minutes, creating displays of remarkable beauty and complexity that demonstrate the dynamic nature of magnetosphere-atmosphere coupling. The seasonal variations in auroral activity reflect both the changing geometry of Earth's magnetic field relative to the solar wind and the varying atmospheric conditions that affect auroral visibility. During equinox periods, when Earth's magnetic field is optimally oriented for solar wind coupling, auroral activity tends to be enhanced. The long polar nights of winter provide the best viewing conditions for aurora, while the continuous daylight of polar summer makes auroral observations more challenging despite continued particle precipitation. as you float peacefully in the soft glow of auroral light. Your consciousness now perfectly attuned to the gentle rhythms that connect solar activity to terrestrial beauty. You begin to sense the deeper patterns that govern our relationship with our star. The solar flares we have followed from their origins in magnetic reconnection to their beautiful conclusion in Earth's aurora represent just one note in a vast cosmic symphony that has been playing for billions of years. The 11-year solar cycle, the longer-term variations in solar activity, and the gradual evolution of our star itself all contribute to rhythms that operate on timescales far longer than human civilization, but that nonetheless influence every aspect of life on our planet. Let your breathing slow even further as you contemplate the profound interconnectedness that characterizes our solar system. The same nuclear processes that power solar flares also maintain the steady energy output that warms our planet and drives our weather systems. The magnetic fields that create spectacular auroral displays also deflect harmful cosmic radiation that would otherwise sterilize Earth's surface. The solar wind that carries flare particles across interplanetary space also shapes the boundary of our solar system and creates the heliosphere that protects us from energetic particles originating in distant stars. The solar cycle itself represents a manifestation of the deep magnetic rhythms that govern our star's behavior. Every 11 years, the sun's magnetic field reverses its polarity, creating a 22-year cycle of magnetic evolution that affects solar activity, cosmic ray penetration into the solar system, and subtle climate variations on Earth. These cycles have persisted for as long as we have records of solar observation, demonstrating the remarkable stability of the dynamo processes that generate and maintain the sun's magnetic field over periods much longer than human history. As you drift peacefully with these stellar rhythms, your heartbeat now synchronized with the patient pulse of solar evolution, you can appreciate how solar flares represent both change and continuity in our cosmic environment. While individual flares are relatively brief events lasting minutes to hours, they occur within the context of magnetic cycles that span decades and stellar evolution that spans billions of years. Each flare contributes to the gradual evolution of the solar magnetic field while participating in the same fundamental processes that have shaped our star throughout its long lifetime. The beauty of aurora serves as a nightly reminder that we live within a star's atmosphere, connected to solar processes by invisible threads of electromagnetic force that stretch across 93 million miles of space. The gentle light dancing in Earth's polar skies carries information about magnetic reconnection in the solar corona, particle acceleration along magnetic field lines, and the protective embrace of our planet's magnetic field. In this way, aurora represents not just a beautiful natural phenomenon, but a visible manifestation of the cosmic forces that have shaped the evolution of our solar system. The gradual transition from solar maximum to solar minimum and back again creates long-term variations in space weather that affect everything from satellite operations to radio communications to the frequency and visibility of auroral displays. During solar maximum, when magnetic complexity peaks and flare activity is most common, aurora can be seen at lower latitudes and space weather effects are enhanced. During solar minimum, when the sun's magnetic field simplifies and flare activity decreases, aurora retreat toward the poles and space weather becomes more predictable. Rest now in the knowledge that you have witnessed one of nature's most complete energy transformation cycles, from nuclear fusion in the solar core through magnetic field generation, energy storage, and reconnection, to particle acceleration and the creation of light in Earth's atmosphere. This cycle represents a perfect example of how energy flows through natural systems, being transformed from one form to another while maintaining overall conservation and creating beauty at every stage of the process. Let your thoughts drift like aurora across the peaceful sky of consciousness, knowing that the same electromagnetic forces that create these beautiful displays also govern the formation of galaxies, the birth of stars, and the complex chemistry that makes life possible. The solar flares we have observed represent local manifestations of universal physical processes that operate throughout the cosmos, connecting our small planet to the larger community of stars and galaxies that make up our universe. As you sink deeper into restful sleep, carry with you the understanding that you are part of this cosmic community made of elements forged in stellar cores, warmed by nuclear fusion, and protected by magnetic fields that demonstrate the elegant way electromagnetic forces organize matter and energy throughout the universe. The gentle rhythm of your breathing joins the eternal circulation of energy that flows from star to planet to atmosphere, creating the conditions that allow consciousness itself to emerge and contemplate the beauty of the cosmic environment that sustains it. Sleep peacefully, knowing that tomorrow the sun will continue its patient work of nuclear fusion, magnetic field generation, and energy circulation that has sustained life on Earth for billions of years and will continue for billions more. The aurora will dance again above the polar regions, carrying the light of our star into Earth's protective atmosphere and creating beauty from the same electromagnetic forces that govern the behavior of matter and energy throughout the cosmos. Dream of magnetic field lines stretching through space like invisible bridges between worlds, of particles dancing along these bridges at the speed of thought, and of the gentle light that emerges when stellar energy finally comes to rest in the familiar embrace of Earth's atmosphere. Rest in the knowledge that you are forever connected to our star through the constant circulation of energy and matter that makes our solar system a unified, living entity where every component contributes to the harmony of the whole. The stellar rhythms continue their eternal dance, carrying the memory of solar flares through the quantum vacuum of space, through the protective magnetosphere of our planet, and into the dreams of those who rest beneath aurora's soft and gentle glow.